the nucleophilic substitution reaction, in this case, you need to have a nucleophile and the substrate. The substrate generally has an alkyl halides. So you need to have a substrate of alkyl halide and the nucleophile. So the nucleophile prefers to attack over the carbon which is carrying the leaving group. The leaving group is this X, we will generally call it as a leaving group, and leaving groups leaves out and forms a new bond between the carbon and the new nucleophile, along with the leaving group leaves out. The alkyl groups can be of methyl, or you can use the propyl iodide. Here in this case, methyl chloride. So the methyl chloride reacts with the nucleophile of OH minus. You can get the product of methanol. Suppose if it is a propyl iodide and treat with the SH minus, then you will can prepare the thiol, corresponding thiols. And suppose if you have a substrate of ethyl bromide, then treat with the methoxy ion, then it will try to attack over the carbon, and the Br will leaves out, you will get an ether. So you can prepare the alcohol, thiols, and ether from this type of substrates. If you have any type of this alkyl halide substrates and the nucleophile, so the nucleophilic substitution reaction prefers to happen over the carbon which is carrying the leaving group. And the leaving group leaves out, you will get the carbon and new bond formation. So based on this nucleophilic substitution concept, SN1, SN2, and SNI has been listed out. SN1 stands for the substitution nucleophilic unimolecular. SN2, the substitution nucleophilic, the bimolecular. And SNI stands for the intramolecular. So, and various concepts we will be covering under this SN1 and SN2, like what is SN1, SN2 definition, mechanism, kinetics, stereochemistry, and the factors influencing the reaction rate. Let's move on to the SN2. So instead of going specifically like taking any random substrate, we will move on to the SN2 mechanism with the specific substrate like methyl bromide. So now methyl bromide is a substrate, and here the one alkyl group CH3, and along with that one leaving group, that is Br. So now if you are trying to react this methyl bromide with the OH minus, so now OH minus acts as a nucleophile, prefers to attack over the carbon which is carrying the leaving group, and you will get an alcohol. This is methanol. Along with that, the Br minus leaves out as a leaving group. Now, the various examples, instead of having the nucleophile of OH minus, if you are using your OH minus and methyl bromide as a substrate, you will get an alcohol as a product. And instead of using OH minus, suppose if you are using RO minus, then RO minus will also act as a nucleophile, prefers to attack over the CH3Br, and CH3OR will be the end product, that is an ether formation. And instead of using this type of nucleophile, if you're planning to use HS minus, then HS minus attacks over the carbon which is carrying the leaving group, then you will get a thiol, that is mercaptan. And instead of using this, if you're using RS minus, then CH3SR, a sulfide formation. And I minus, if you're using as a nucleophile, then the halogen exchange reaction, I minus will replace this Br, and you will get the alkyl iodide. Instead of using this I minus as a nucleophile, if you're planning to use a neutral nucleophile NH3, then NH3 will prefer to attack over the carbon which is carrying the leaving group, then you will get CH3, NH3 plus, and alkyl ammonium ion. Instead of ammonium, suppose if you are planning to use them in water, and then this water will also act as a nucleophile, prefers to attack over the carbon, which leaves out the leaving group, and you will get alcohol after the proton deprotonation or deprotonation step. So the various products can be prepared just by having only a simple example of methyl bromide, that is alkyl bromide. And just by changing the various nucleophilic systems, you can prepare the various type of products, starts from alcohols to and alkyl ammonium ion. So coming to the mechanism part of SN2, the nucleophile and alkyl halide combines to form a penta-coordinated transition state. In this case, you need to have a transition state wherein the carbon has a 5 bonds. So that's why pentacoordinate transition state formation is the rate determining step in the SN2 mechanism. So OH minus nucleophile, and this will act as a substrate. So the methyl bromide is a substrate, and this will be the nucleophile. So now, if your nucleophile attack over the carbon, and there is an existence of transition state for a while, the transition state with a simultaneously bond breaking and bond forming takes place in this particular step. So the OH minus generally has a partially negative charge, and the Br which is present over the carbon, the Br will also carry a partial negative charge. So the partial negative charge is resided over the leaving group and the nucleophile, and carbon is now it's an electropositive. Now this state is some pentacoordinated carbon, pentacoordinated transition state formation is this one. In this case, the CBr bond is going to break, and the new bond of a CO bond formation is taking place in this particular transition state. If it is the CBr bond breakage taken place completely and a new bond formation of a CO bond happens simultaneously, then only you can expect this an alcohol formation. Along with that, Br minus, Br will leave out as a Br minus. So the two species, the Rx and the nucleophile is present in the transition state. The dotted lines indicates the partially formed or partially broken covalent bond. So the partially, these two actually, the bond breakage between the CBr and the bond formation do happens between the carbon and the oxygen. Now it is clear that you need to have a nucleophile and the substrate of methyl bromide, or you can use an alkyl that is primary alkyl bromide for this SN2 kind of reaction. The transition state needs to be formed, and this is the transition state is the rate determining step, and after that only you will get the expected product of alcohol. So the conversion of alkyl halides to alcohol. Now kinetics, the study of rate of reaction is called N kinetics. The reaction involves the transition state in which both the reactants Rx and OH minus are together. So if you're looking to the transition state, in this case, you have a nucleophile as well as the substrate, right? So the reaction involves a transition state in which both reactants and the nucleophile are together. That's why the rate is equal to small k into concentration of Rx into concentration of OH. So the substrate and the nucleophile plays an important role in case of SN2 reaction. So if you want to rate determining step, and the rate is generally dependent on these two, like substrate and nucleophile. That's why rate is equal to small k, rate constant, into concentration of Rx into concentration of OH. Rate is dependent on the concentration of the two species, that is alkyl halide and the NaOH. Suppose if you are using nucleophile of OH minus from the NaOH, then these two will be acts as a concentration of alkyl halide and the concentration of OH minus or NaOH. So it is clear that the rate is equal to small k into concentration of Rx into concentration of OH. So now, so far we have explained only with respect to the simple system of methyl bromide. Do you think this methyl bromide is a chiral or optically active substrate? Methyl bromide has any chirality?
No, sir.
Okay, so can we call it as an optically active substrate?
Yes.
No, sir.
Yes, sir.
It's a chiral.
Is it a chiral or a chiral?
It's a chiral.
It's not chiral.
It is not a chiral.
A
Why?
chiral.
It is a chiral. Why? The carbon?
Because there are three same group are present over
Yes.
the carbon.
Same group, that is HHH is present over the carbon. So this system is not a optically active substrate. So in this case, suppose even though OH minus is attacked over the carbon, and you can expect only one type of alcohol only. as it is not an optically active substrate. What will happen, suppose if you have an optically active substrate, then if you're trying to perform the nucleophilic attack over the carbon which is carrying the leaving group, and this has a chirality. So the substrate, if it is has a chiral center and the substrate is optically active, then comes is stereochemistry. So in case of stereochemistry, the transition state of SN2 reaction has a planar arrangement of carbon atom and the remaining three groups. So the occurs with inversion of chiral center called Walden inversion. I think one of you has said about the Walden inversion can be expected in the SN2 reaction in the last class, right?
Yes.
Yes, so Walden inversion, if you want to notice this kind of Walden inversion, then the substrate needs to be taken is an optically active substrate. If it is not optically active substrate like methyl bromide, if the nucleophile prefers to attack over the methyl bromide, then you can expect only a methanol. So no stereochemistry with respect to the formed methanol. But instead of having an optically active substrate, if you are having an optically active substrate, then comes is like what type of inversion one can expect. In this case, the CH, H, and CH2, right? So this will act as a nucleophile, and nucleophile prefers to attack over the in tetrahedral geometry. The carbon is in tetrahedral geometry, and so during this reaction, the nucleophile prefers to attack over the carbon. Wait, so this is not optically active substrate. Do you think this is optically active substrate?
No, sir. It's optically inactive.
This is optically inactive. Let us assume. So in the previous example, we have only the methyl bromide. Now, the one of the H has been replaced by one methyl. So this is an example corresponds to ethyl bromide. In this case, the carbon has two hydrogen bond and one methyl group, along with that one leaving group of Br. In this case, the nucleophile, the red dot represents the nucleophile, and this particular portion will represents to the substrate. This is the leaving group and this is the carbon, and wherein you have a substituents on the carbon. In the SN2 fashion, the nucleophile prefers to attack from the front side or back side.
Backside.
Backside.
Yes. So why it is prefers to attack from the back side? Why not from the front side of the where the leaving group lies to leave salt? So now in this case, let us assume this is the nucleophile, and this is the carbon, and this is the leaving group. Now there are two openings where the nucleophile can approach, right? One is from the back side with respect to the leaving group's leaves out, or from the same side of the leaving group's leaves out. Also, there is a possibility to attack over the carbon. Why it prefers to attack from the back side rather than from the front side attack? Any reason?
Steric hindrance.
Steric hindrance, right? Okay, then anything else? Br is bulky group, of course, steric hindrance, fine. Next. What charge usually the nucleophile prefers to have it?
Negative.
Negative. And suppose you have an electronegative, the carbon is more electronegative, or the Br is electronegative?
Bromine.
Okay.
Br.
So bromine is electronegative, right? So now what type of charge one can notice over the carbon as well as on the bromine atom?
Partial positive and negative
Yes,
charge.
partial positive charge over here and partial
Positive
negative charge. What it represents generally?
Negative.
Means electron density is more over carbon or electron density is more over bromine?
In bromine, sir.
Yes, electron density will be more over the bromine system, right? So now let us assume the electron cloud is more towards this, and you have a nucleophile. It is also has an electron density. The both are negatively charged. Do you feel that the negatively charged can easily approach from this side to attack
No,
over this particular carbon?
No,
Because
sir.
you know that like
No, sir.
charges,
There will be electrostatic
Repel
repulsion.
each other.
yeah, so like charges generally repel each other and unlike charges attract each other, right? So in this case, as it is negatively charged, and this is also to prefers a partial negative charge because of the electronegative difference between the carbon and the bromine, that this prefers not to prefer to attack the carbon from the same side of the leaving group leaves out. Instead, the backside attack here, there is no steric hindrance or electron repulsion caused by the any of the substituent which is present over the carbon, and it can easily approach the carbon side, the carbon which is carrying the leaving group from the back side rather than from the front side. During the approaching of this nucleophile over the carbon from the backside attack, you need to have attain a transition state. In the transition state, if you look into this transition state, the electron density is slightly less over the carbon, and electron density will be more over the nucleophile, and electron density will be more over the BR system. That's why the partial negative charge happens over the nucleophile, and partial negative charge do happen over the bromine atom. This is a planar transition state, and in this case, there is a new bond establishment between the carbon and the oxygen, and the bond breakage between the C and Br system. Once this state, transition state, is over and it overcomes from the bond breakage and bond formation process, then only you can expect the tetrahedral geometry, and which corresponds to the alcohol. Here you are converting the alkyl bromide, that is of primary alkyl bromide we have taken. In the previous example, you have taken an example of this methyl bromide, and suppose if you have a methyl substituent here, that is ethyl bromide, then you can expect one of the system over ethyl, right? So rest will be just inversion of configuration. But as it is not optically active, you cannot distinguish the formed product. Let us look into the optically active substrate. So optically active substrate, this is whether it is optically active.
Yes, sir.
Here the carbon has CH3 and the C2 CH2 CH3. This is also a different group, and CH3 different group, and then H is also different. And yeah, so the carbon now, the name of this substrate, CH3 CH. In the second position you have an iodo group, and CH2 CH3. Name of this substrate, 1 2 3 4 4 carbons. The second
2
carbon,
iodobutane.
yes, 2 iodobutane. So the 2 iodobutane is the substrate, and this is actually optically active and chirality because of this carbon has a chiral center, and this substrate now acts as an optically active substrate. And SH minus you are using as a nucleophile. The SH is now in this case to the SN2 mechanism. In the SN2 mechanism, the SH minus prefers to attack from the back side and attack over the carbon, and simultaneously the Ci bond breakage, and you will get a CSH form. The bond to the nucleophile in the product is always on the opposite side relative to the bond to the leaving group in the starting material. So prefers to attack from the back side, and bond formation happens between the carbon and the sulfur, and the bond breakage is taken place between the carbon and the iodo. This is in case of SN2. And during this optically active substrates if you are having, then the configuration will change. Suppose if you have an R configured starting material, then as it is prefers to attack from the back side, there is an inversion of configuration. So the end product of thiol generally has an S configuration. Suppose if you have start with an optically active S, then you will get R. So the product is have an inversion of configuration in case of optically active substrates. Suppose if you are taking an optically active alkyl halide as a substrate and you're trying to perform an SN2 reaction, then you can expect the inversion of configuration because of the nucleophile prefers to attack from the opposite side to the bond breakage between the carbon and halide system. In case of okay, now it's clear with SN2.
Yes, sir.
Yes.
Okay, so
Yes, sir.
some of the points you need to remember that what type of substrate, what type of alkyl halides, and whether it is rate of reaction is dependent on both the substrate and the concentration of the nucleophile. Then transition state formation is the intermediate step, and during the transition state the carbon has a penta coordination state, and a partial negative charge occurs on the nucleophile as well as on the leaving group. This is in planar transition state formation, and nucleophile prefers to attack from the opposite side from the where the leaving group leaves out. And you will, if an optically active substrate if you are taking, then inversion of configuration. Let's move on to the SN1. Then you will get a better clarity how SN1 and SN2 are can be differentiable. SN1 is unimolecular nucleophilic substitution. In this case, let us take an example of solvolysis of tertiary butyl bromide to give an tertiary butyl alcohol. This is a structure of the tertiary butyl bromide. And solvolysis is the step. Solvolysis means you need to use
Solvent.
solvent. So here actually H2O. In this case, you will get plus along with this alcohol and HBr. Okay, so what type of mechanism one can expect it in case of SN1? SN1 is unimolecular nucleophilic substitution. There are two steps in this reaction in order to convert from alkyl bromides to alcohol. But in case of SN2, there is a single step reaction, that is through transition state formation. In this case, if it is in SN1, you need to have a two-step reaction. The step 1 involves the leaving group dissociates to form a carbocation. The step 1 is generation of carbocation. So how to generate carbocation? You need to, as it is, you are performing the reaction in polar protic solvent, the dissociation of CBr bond will take place, and you can generate the carbocation. The intermediate in this SN1 reaction is the carbocation intermediate, is the reaction intermediate. It is a carbon is trigonal planar, and if you are looking into this, is a trigonal planar structure, the formed carbocation. And the first step is the slow and the rate determining step. Means dissociation of CBr bond, heterolytic cleavage of CBr bond is the slow step and the rate determining step, and the generation of carbocation intermediate. In this state, you have a carbocation species as well as Pr minus. This is the leaving group. So the substrate is this one, and the slow and the rate determining step is the step 1, generation of carbocation and leaving group. The step 2 is the reaction of carbocation. The reaction of carbocation. So now the carbocation is an electrophile with water, acts as a nucleophile, gives an oxonium ion. In this case, the step 2 is actually you will be having a carbocation. Along with that, the water molecule. The water molecule will act as a nucleophile. The oxygen has a 2 lone pair, and one of the lone pair prefers to attack over the carbon and try to establish a new bond between the carbon and the oxygen. The one thing you need to be clear here in this particular trigonal planar structure of carbocation, the OH, that is H2O nucleophile, can attack from front side or from the back side. So there will not be any stereochemical issue with respect to this intermediate. The OH minus, the H2O, if it is attacks from the front side, then you will get this particular form of the alcohol. Instead, if it is the H2O is prefers to attack from the back side, then you will get this configured substrate, that is oxonium ion formation. And this is actually a fast step, the fast step. So the previous step was the slow step and the rate determining step. The H2O attack over the carbocation is the fast step. You can get the oxonium ion. The two forms of oxonium ions one can get. So the last step of the reaction is step 3, wherein the proton transfer completes the reaction. Here the water molecule deprotonates the formed oxonium ion, and the step is fast step reaction. We will get the alcohol as an end product. So this is related to the SN1 mechanism. So it involves a 3-step mechanism. And to sum up, SN1 is a first order, and SN2 will follow a second order kinetics. SN1, usually the rate is equal to K into concentration of Rx. And in case of SN2, the rate is equal to K into Rx into concentration of the nucleophile. Here in the last part of the last class, we were discussing about the energy level diagram corresponds to the SN1 and SN2. In case of SN1, as it is a two-step reaction, and you can notice that a two energy profile, that is one hump corresponds to the step 1, where the generation of carbocation, and then next is nucleophilic attack over the formed carbocation will lead to the formation of product. And the energy level difference between the first step and after the product formation, the energy of the product is lower than the starting two reactants. And similarly, in case of SN2 mechanism, the SN2 is a single step reaction and it proceeds by a transition state formation. And this particular point will be corresponds to the transition state formation, wherein the carbon is penta-coordinated, and both the incoming nucleophile and the leaving groups is present in this transition state. And the nucleophiles will has a partial negative charge, and the leaving group will also have a partial negative charge. And once that is transition state over, then the bond breakage of the CBr bond will take place effectively, and the new CO bond formation takes place in this case, which result to the formation of corresponding alcohol and the leaving group. Now let's move on to the stereochemistry of this particular SN1 and SN2. In case of SN1 mechanism, let us take the optically active substrate or enantiomer. The proceed partially racemization and some inversion. In case of SN1, as it is a two-step reaction, the first step is the rate determining step, and formation of planar carbocation is the intermediate. The racemization, why you will get generally this kind of reaction. Nucleophile needs to attack over the formed carbocation, and then you will get the two types of enantiomer. The nucleophilic can attack from either face of the planar carbocation intermediate. In this case, the intermediate is the planar carbocation intermediate, and the planar carbocation is an achiral in nature. But the one you have taken as a starting material, that is chiral or achiral. The substrate is a chiral or achiral?
Chiral.
It is a chiral, right? So it has a leaving group of Cl, and then this is the carbon, and the C6H5, one is C6H5, another one is the chlorobenzene, and HM. So the carbon is substituted by the 4 different group, and it has a chiral center. Now, in this case, the first step during this reaction is the formation of a planar carbocation. So in the planar carbocation state, it has an empty p orbital, and all the substituent which is present on the carbon is in the same plane. So because of that, it has a chiral. It is not a chiral now. Now, once you get this intermediate planar carbocation, then comes is the attack of nucleophile. In this case, we are using the methanol as a nucleophile, and the nucleophile means the oxygen has a two lone pair, and it prefers to attack over the formed carbocation, that is the planar carbocation. It can attack from the two different manner, either from the same side of the leaving group leaves out, or from the opposite side of the leaving group leaves out. So that is, we will call it as a front side attack or back side attack, which results into the formation of two types of enantiomers. One is some S form of enantiomer, and another one is the R form of the enantiomer. The resultant will give you an racemic mixture, because if you have both the proportionate enantiomer R and S in equal proportionality, then we will call it as a racemic mixture. This is happens only in theoretically. That means there is no approach of nucleophile before the formation of carbocation, or till the anion pair formation is still existed. In such cases, if it is nucleophile is prefers to attack not from the same side of the leaving group, it prefers to attack from the back side of the leaving group leaves out. So in such cases, generally you will be having an inversion product is slightly excess over the retention of configuration. That's why the racemization as well as some inversion is the proportionate generally you will expect in case of SN1 reaction. The leaving group will tend to block approach of the nucleophile, leading to more inversion than the retention for the SN1 reaction. Because in this case, try to visualize that you have a different R1 and R2 substituent. Along with that, there is a small sized hydrogen atom, and this is in planar carbocation now state, and the nucleophile is just trying to leave out from this particular side. The leaving groups in this case is Cl minus, and now the nucleophile has an easy approach from particularly from this particular phase, not from the either from this side or from this particular position, because here you have a leaving group trying to leave out from the system. The approach of the nucleophile from this side is less hindered, because though there is no hindrance caused from any of the group which is present over here, the nucleophile can easily approach this particular site from this particular um, side. But if it is having a nucleophile, the both are negatively charged. The leaving groups is also negatively charged, and Nu minus is also negatively charged. In such cases, Nu minus needs to overcome from the repulsive effect caused by this leaving group and then try to approach this particular site. But this is actually highly difficult when it is closely associated between this carbocation and the Cl minus. Approach of the nucleophile from this side is partially blocked because of the Cl minus, which remains associated with the carbocation as an ion pair. Because during this dissociation of the carbon and the Cl bond, even though the bond between the C and L breaks down, it not immediately gives an free ion states like carbocation and the Cl minus. For a for a while, it will be in a form of intimate ion pair. Intimate ion pair is nothing but the carbocation and the Cl minus. The bond between these two will be dissociated, but it tries to have the positive charge and Cl minus. The both is trying to interact as a neighboring groups. It is not completely free carbocation or Cl minus state. In such cases, the incoming nucleophile cannot approach the Cl, the formed carbocation, particularly from the same side of the leaving group leaves out. In such cases, the nucleophile prefers to attack from the backside because there is no hindrance. So as soon as it dissociates from the intimate ion pair, and you will get a free ion state, like free carbocation and the leaving group of Cl minus. In such cases, there is a two possibility. The nucleophile can attack from the same side or from the back side. In such cases, generally you expect the racemization, means 50% and 50% of the formation of the R and S. So SN1 in reality, the formation of ion pair. So how usually the ion pair is formed during the SN1 reaction? Take the example of optically active substrate. Then this state is a carbocation state. It carries a positive charge. And this is the leaving group, wherein in this particular state, the carbon and the leaving group bond has been break down, and still it is not completely out of this area. So in such case, the nucleophile is prefers to attack from the backside, from the where the leaving group tries to leaves out. And this particular form, we will call it as an ion pair state. This ion pair means the carbocation as well as the leaving group is not completely in the free state. Still, it has a certain kind of interaction, and this leaving group tries to leaves out. And the nucleophile, in such cases, the nucleophile prefers to attack from the backside. Okay, this is the ion pair state. So during this particular, whenever the carbocation and the leaving group are in ion pair state, then the nucleophile prefers to attack from the backside. Always you will end up with the inversion product, because this flipping the nucleophile, if you have an R configured here, and then after the nucleophile prefers to attack from the backside, and you will get the S configured optically active substrate. And this state will also be there as one of the steps before it is moving into the free carbocation state. So once you get in free carbocation state, then the nucleophile which is available in the reaction medium can approach the carbocation in any other way. Like it can try to attack from the back side, or it can also try to attack from the front side, because there is no hindrance from this leaving group, because the leaving group is already leaves out from the carbocation, and now the carbocation is free, and the incoming nucleophile can attack any of the from either from the any of the faces, front side or from the back side. If the nucleophile tries to attack from in this particular stage, then you can expect the racemization. Means the backside attack generally will give the S form, and if it is try to attack from the front side, then retention of configuration or so. In this, if you are seeing the whole process, if suppose let us assume as soon as the carbocation is formed, there will not be any ion pair stage. Let us assume for a while you don't have the ion pair stage. In such cases, what will happen? Straight away there is a possibility it will go to the free carbocation state, and there is an attack of nucleophile from the both the side. Resultant should be always racemization, means you can expect the 50% of this S form, and the 50% corresponds to this. But whenever you're determining the reaction and the R and S configuration after the reaction, generally you have an S form slightly more in proportionate over the R form. Then they came up with an idea that, okay, this will follow with the ion pair form. Then it will move to the free carbocation state. So as and when it is in ion pair state, the nucleophile always prefers to attack from the backside, not from the front side. In such cases, you will get some amount of S inversion already. Then as soon as this dissociates and you will get in free carbocation, then possibility is the R and S in equal proportionate. But this can happen only in theoretically, like as soon as the bond dissociation takes place and move on to the free carbocation state. But in reality, whenever you have you're using a solvent and nucleophile and the reagents, in such cases, the nucleophile always the dissociation of the carbon and the leaving group will takes place, and it tries to move in an ion pair form. After that, it will move to the free carbocation state, After that, you will get the racemization. And before moving into the free carbocation state, in the ion pair state, always you prefers to get an inversion product. Now, let us take a live example for this, like how the S proportionate and R proportionate is varied with respect to the optically active substrate. Now, take this as an optically active substrate, wherein it is the substrate is in R form. The 6-chloro, the 6-chloro, the 2,6-dimethyl octane. So now you know that this is chiral carbon and it's optically active and it exists in the R form. Now you are trying to perform an SN1 reaction on this particular substrate. Take the alcohol in ethanol medium, means polar protic solvent you are using. In such cases, nucleophile is OH minus, and you will get the Cl will be substituted by the OH. The resultant will be alcohol. Conversion of alkyl halides to the optically active alcohol. So you're starting with the optically active alkyl halide and trying to convert it into optically active alcohol. But after the reaction, you will have a proportionate of S form of 60% and R form of only 40%. That means the 40% of R and the 40% among the 60 will be 40%. That is equal to the free carbocation state. After that, you will get the 40% of S and R. The whatever the rest 20% will be formed during the ion pair stage. Is it clear? So it will be generate 20 plus 40, you can call it. The 20% of the inversion is preferred during the ion pair stage itself, because in such cases the Cl bond dissociation and the leaving group is in ion pair stage, and the nucleophile of OH minus in such cases prefers to attack from the backside, which leads to the S, that is inversion product. And once the dissociation of this carbon and Cl happens, and then after that you will get a free form of the carbocation, then rest of the 40% and 40%, 40% of the S and 40% of the R form. Is it clear? Any doubts with respect to this?
No, sir.
Okay. So that's why always if you are taking optically active compound, in particularly SN1 reaction, you will have an inversion product slightly excess along with the racemization. Next, coming to the factors which affects for the SN1 reaction, the factors influencing the rate of the reaction in case of SN1 and SN2, the effect of substituent and nature of the nucleophile, nature of the leaving group, and the solvent effect. The effect of substituents on SN1 reaction, in case of SN1 reaction, governed by electronic factors, namely the relative stability of the carbocation intermediate. So you know that the carbocation stability, so the order of carbocation stability starts from the tertiary carbocation, then secondary carbocation, then primary, and the methyl will be the last one. Now, this is a tertiary carbocation, the substrate which has a tertiary carbocation. In this case, you will be having R, R, R. There are 3 R groups, and R acts as a plus I inducing groups. So plus I means plus inductive effect inducing groups. There are 3 R groups are present over here in tertiary carbocation, and the carbon carries a positive charge here. And because of the electron donating effect of these 3 R groups will stabilize the formed carbocation. And this is more favored for the SN1 reaction. If you have a substrate of this kind of tertiary carbocation forming as an intermediate during the reaction, and such substrates are more preferred for the SN1 reaction. Next is 2 electron donating effects can be noticed in case of a secondary carbocation. So in secondary carbocation, you have the carbocation carries in two R groups and plus I effects in this case induced by the two R groups. Now, this stability is less compared to the tertiary carbocation stability. And if you move on to the primary carbocation, as it is two hydrogen atom attached to the carbon and one R group, that is some electron donating group present over the carbon, the plus I effect inducing group is now only one. In this case, there are two plus I inducing group, and in this case, plus I inducing groups are three. In such cases, the primary carbocation is compared to the tertiary carbocation and secondary carbocation, the primary carbocation is quite less stable, and the primary carbocation substrates generally won't proceed via SN1 reaction. So you can expect the SN1 reactions to perform over the tertiary carbocation and the secondary carbocation, but not over the primary carbocation. And that's why the primary carbocation is unfavorable. In this case, if you are looking into this carbocation stability, the overlap from the sigma bond into the vacant p orbital will take place. So the order of substrate in this case tertiary, secondary, and the least will be primary or methyl. The SN2 reactions are governed by the steric factor. On the other side, if you are dealing with the substrates which are related to the SN2 reaction are governed by the steric factors, namely the relative ease of approach of the nucleophile to the site of the reaction. The relative rates mainly deals with in reverse order than the SN1 substrates. In this case, the first priority will be given to the methyl, then primary, secondary, and tertiary. So the methyl primary substrate, secondary substrate, tertiary substrates are the order of these substrates in case of SN2 reaction. Let us take this ethyl bromide as a substrate. In this case, the carbon, and this will be the leaving group attached to the carbon, and the carbon has a two hydrogen atom and then methyl group, which is present in over the carbon. In such cases, less crowding, easier access to the backside of the haloalkane. That means the nucleophile can easily approach from the backside, and because you don't have any hindered group which hinders the approach of the nucleophile from this particular side. If you move on to the tertiary butyl bromide, in this case, it is an tertiary butyl bromide is an has an carbon, and this is the leaving group, and the three methyl group are present over the carbon which is carrying the leaving group. The more crowding can be experienced by the nucleophile, the blocks the access to the backside of the haloalkane. That's why the nucleophile cannot easily move and proceeds via SN2 reaction in case of these kind of substrates. So tertiary or even in case of secondary is quite possible, but the maximum hindrance caused by the tertiary substrates for the SN2 reaction. So now the suitable substrates are methyl halides and primary based halide substrates are first preferred over the tertiary halides. So the bromo ethane, and this is 2-bromo 2-methyl propane or tertiary butyl bromide. So one can easily notice that how usually steric factor influences to proceeds via SN1 reaction or SN2 reaction. So in SN2 fashion, you need to have a less steric interaction towards the nucleophile, because nucleophile needs to approach from the backside and the leaving groups needs to leave out from the front side. The SN2 reaction is fastest with unhindered halides. Unhindered halides means you need to have a primary substrate or methyl halide. So in case of methyl halide or primary halide, so preferably SN1 reaction doesn't happen always. The preferably it proceeds via SN2 fashion. So this trend shows that from if you have a substrate of secondary substrate or tertiary halide substrate, it prefers to proceed via SN1 fashion. And as and when you have a substrates of primary and methyl, the nucleophile attacks over the carbon and prefers to proceeds via SN2. So these two substrates are generally preferred to proceed via SN2 reaction, and these two proceeds to via SN1 reaction. But if you're planning to proceed in reaction of SN2 fashion over the tertiary carbocation, generally doesn't never happens over this tertiary carbocation, tertiary alkyl halide substrate. Similarly, the SN1 reaction cannot be expected over the primary and methyl based substrates. So, is it clear?
Yes, sir.
Okay. Now, let's move on to the nucleophile nature. The nucleophile is neutral or negatively charged Lewis base. You can use the nucleophile either in the negatively charged form or the neutral. Neutral example is you can use the NH3. The anions are usually more reactive than the neutrals. So anions means negatively charged nucleophiles are more reactive towards the SN1 and SN2 reaction over the neutral charged nucleophiles. The more basic nucleophile react the faster. More the nucleophilicity, then the reaction will be the faster. Better nucleophiles are lower in column of the periodic table. The order of nucleophilicity, the NH2 minus has a greater tendency to access a better nucleophile, then followed by RO minus, then OH minus, RNH minus, ARO minus, NH3 minus, then the pyridine F minus H2O. This is the order of the nucleophilicity. Suppose if you are using an NH2 minus as the nucleophile, then you can expect the better reaction rate over the H2O if you are using as a nucleophile. Later on, you can also follow some trend based on the usage of solvent as well. If suppose if you are planning to use I minus in polar protic solvents, polar protic solvent example. Example for polar protic solvent. Protic solvents. Any idea? Polar protic solvent.
Is it water?
Which can act as a polar protic solvent?
Water.
Okay, next. Any other solvents can be used as a polar protic solvent? What about methanol, ethanol?
Sir, I think so, sir.
Yeah.
Yeah.
Yeah, polar protic solvents. You can use the methanol or ethanol also as a polar protic solvent. Fine. In case of so if you're using the order of nucleophilicity, it starts from the NH2 minus and the H2O will be the in this particular trend. The H2O is the less nucleophilicity over the NH2 minus. And suppose if you're suppose if you're planning to use I minus, Br minus, Cl minus, and F minus in polar protic solvents, in such cases, the trend is always the I minus, Br minus, and Cl minus, and F minus. So in this case, the trend is based on the usage of solvent, polar protic solvent. Suppose the same reaction, I minus, you are trying to use it uh, as a nucleophile for the nucleophilic substitution reaction. And instead of using the polar protic solvent, you are planning to use an aprotic solvent. Then the trend will be reversed from I minus to F minus. So in such cases, F minus will be now is a better nucleophile for the nucleophilic substitution reaction over the I minus. And F minus have a better nucleophilicity, then Cl minus, Br minus comes the later stages, then I minus is the least in the aprotic solvent. So that's why it also states an information that type of solvents needs to be used for the nucleophilic substitution reaction, and which also influences over the nucleophilic ability to attack over the substrate, the carbon which is carrying the leaving group. And the I minus, Br minus, Cl minus, F minus trend in polar protic solvent, and reverse trend can be noticed in case of aprotic solvent. Now, the stability of the leaving group is also plays an important role in finding out the nucleophilic substitution reaction. The stable anions that are weak bases are usually excellent leaving groups and can delocalize the charge. So that's why you need to have a stable anions. The weak bases are usually the excellent leaving groups and can delocalize the charge. During the nucleophilic substitution reaction, in an SN2 fashion, suppose the nucleophile needs to attack from the leaving group leaves out, back opposite to the leaving group leaves out. The carbon now has a partial positive charge, and the leaving group will has a partial negative charge, and the nucleophile prefers to attack over the carbon which is carrying the leaving group. Strong base is equal to good nucleophile. Suppose if you have a strong basic character of this, then the good nucleophilicity can be expected. During this case, what will happen? So during the transition state needs to be attained. Nu minus is the partial negative charge, and the ligand needs to lease out as a partial negative charge only. And if you see the transition state image, in this case, the new bond is trying to establish between the carbon and the Nu that requires a stronger bonding, and the bond breakage is happening between the carbon and the ligand. In this case, that requires a weaker bonding between the carbon and the leaving group. Then only the dissociation of carbon and L can easily taken place, and the new bond is easily forms between the carbon and the Nu. So the requirement is there is a strong interaction between the carbon and the Nu, and the weaker bonding needs to take place between the carbon and the leaving group. Then only you can expect the SN2 product. And the L minus, because L minus is trying to leaves out as a L minus. So L is prefers to leaving group is prefers to leaves out as a L minus. It should be had a weak base. So in case of nucleophile, it should be strong base and good nucleophile, and the ligand should be weak base and good leaving group. The leaving group should be good leaving in nature, and nucleophile needs to have a good nucleophilic character. Then only the bond breakage and bond formation can take place in the SN2 reaction. The relative reactivity corresponds to this has been listed out here. The OH minus, NH2 minus, OR minus will be not that much having the relative leaving ability. But if you are using the F minus, Cl minus, Br minus, or I minus, or tosylated functional groups, O minus. In such cases, the first priority can be given to this TO as O minus tosylated functional groups as a leaving group. Because these groups, if it is present in the place of L, TO as O minus tosylates, tosylates are generally a better leaving group over the if you are using OH minus, NH2 minus, or OR minus, because this won't prefers to undergo the C and the leaving group bond breakage, and it won't easily form convert the corresponding starting material into the product formation. But as soon as you're using the L position with this tosylates, or if you are using in a bulky leaving group I minus, there is a possibility that the leaving group can easily leaves out, and the incoming nucleophile can easily attack over the carbon. And this is the rate of reaction values found during the reaction. If you are using a substrate which is having a tosylate functional group, then the rate of reaction will be very fast. Then if you have an alkyl halide, alkyl iodide particularly as a substrate, then this also proceeds in a moderately good way for the SN2 reaction. Then comes this Br minus, Cl minus, the least reactivity. F minus is also least, and then the very negligible reactions can be noticed whenever you have a substrate carries an OH or NH2 or OR as a leaving group. So from here to here, if you are moving, the rate of SN2 reaction increases. This is based on the nature of the leaving group. So you need to have always keep it in mind. The leaving group should be a good leaving group, and excellent leaving groups are generally the weak bases. If you are using a weak basis, then you can expect the better leaving group ability. Then comes to the solvent. The role of solvent on SN1 and SN2 reaction. Generally, in SN1 reaction, the protic solvents will be preferred. The solvent that can form hydrogen bonds like the OH, NH, these solvents favor SN1 reaction. The greater the polarity of the solvent, the easier it is to form a carbocation in it. So why you are using protic solvent? The protic solvent you are using because to easy formation of carbocation in the first step in case of SN1 reaction, and later on stabilization of the formed carbocation. So for that you need
It can easily donate proton.
yeah, it will usually donate the proton, and thereby it stabilizes the formed carbocation. That's why you need to use always protic solvent. The protic solvents, if you are using in SN1 reaction, that is favored over the aprotic solvent. Then greater polarity of the solvent, easier is the formation of carbocation during the reaction. Instead of using protic solvent, you are planning to use an aprotic solvent. Generally, the aprotic solvent does not have OH or NH functional group. Then there is no question of hydrogen bonding, and it favors always the SN2 reaction. Means in there is no it is a single step reaction. There is no formation of carbocation. There is no carbocation formation of carbocation, and absence of OH or hydrogen bonding donating ability from the existed solvent. Thereby, there will not be any influence of the solvent over the incoming nucleophile. It is more difficult to form carbocation in aprotic solvent. That's why the aprotic solvent is not the preferred solvent because it cannot easily influence for the carbocation formation. That's why the aprotic solvents favors the SN2 reaction over the SN1 reaction. Let us take an example of this. The bromobutane, and trying to use a nucleophile of N3 minus azide based nucleophile N3 minus. Then in this case the CH3 CH2, you are converting this, replacing the Br with the N3, and the Br minus is in leaving group. The same reactions can be performed under various solvent systems. Start from methanol, water, DMSO, DMF, then acetonitrile, then HMPA. So in such cases, you're changing the solvent but keeping the two reactants for the reaction same, and you're expecting this product to form. The relative reactivity is dependent on the solvent here, because you are trying to keep the two reactants and the reaction medium in the same manner. but only thing is you are trying to change out the solvent. So you have used the protic solvents, that is in case of methanol and water. DMSO and DMF is example corresponds to aprotic, polar aprotic solvent, polar aprotic solvent. This is polar protic solvent, and this can be an aprotic solvent, acetonitrile and HMPN. So in such cases, the reaction, this needs to proceed via SN2 reaction only, as it is an primary carbocation, a primary carbon based alkyl halide, and it tries to proceed via it tries to process via the SN2 mechanism. If you are trying to perform the reaction over these two reactants in methanol, the relative reactivity is 1. And if you are changing from methanol to water, then 7. DMSO means if you are changing the instead of using the polar protic solvent, you are planning to use a polar aprotic solvent. In such cases, the SN2 reaction is more favored. In this case, 1300 is the relative reactivity. Then if you move on to the DMF, then 2800 is the relative reactivity. And still, if you're moving towards the non-polar solvent, because here it is polarity is high, and if you're moving to this acetonitrile and HMPA, the polarity will be in the lower side, and you can expect a better SN2 conversion rate with respect to the non-polar solvent or not polar, non-polar aprotic solvents. So acetonitrile and HMPM, so you can expect 5000 the reactivity, and 2 lakhs reactivity corresponds to the HMPA solvent. So in solvent effect, the solvents that can donate hydrogen bonds like OH or NH slow SN2 reaction by associating with reactants. Energy is required to break the interactions between the reactant and the solvent, because all bond breakage and bond formation needs energy, and these energies generally will be extracted from the solvent systems. The polar aprotic solvents, NH, OH, or SH based solvents, if you are using, form weaker interaction with the substrate and permit faster reactions. NH, the same substrate once again, and solvent reactivity has been discussed here. There is the same values, and like the X minus is the nucleophile, and usually if you're using the polar protic solvent, the nucleophile will be stabilized by the hydrogen bonding interactions between the polar protic solvents. That's why you can expect the reactivity of 1 and 7 in this case. As soon as you are changing the polar protic solvent and then trying to use a polar aprotic solvent, the reaction rate is enhancing. So 1300, 2800, and then if you are using in a slightly non-polar systems, then you can get a better reaction rate. Okay, so let's move on to the aromatic nucleophilic substitution reaction. In this case, the principles, there are 4 principal mechanisms for aromatic nucleophilic substitution, which are similar to that of the aliphatic nucleophilic substitution reaction, because so far we have discussed with the aliphatic alkyl halides. Then the nucleophilic substitution with respect to SN1, SN2 has been discussed, and the effect of solvent, effect of substrate, then role of solvent, energy profile diagram corresponds to SN1 and SN2 reaction, and what and all the steps used involved during the SN1 reaction and SN2 reaction is forward. Let's move on to the aromatic nucleophilic substitution reaction. Here, there are certain concepts like SNAr mechanism, SN1 mechanism, and Benzyne mechanism, and SRN1 mechanism can be discussed. But the substrates what we are using is some aromatic based halide systems. So in case of SNAr mechanism, nucleophilic substitution aromatic mechanism, the introduction of electron withdrawing group, we will represent it as a EWG in the substrate, and LG is the leaving group. And trying to perform over the aromatic based leaving groups, alkyl halides, on the aromatic nucleus makes the system susceptible to nucleophilic attack. The mechanism is similar to that of the electrophilic substitution, except that an anion rather than the cation intermediate is involved. In case of electrophilic substitution reaction, generally you will get an cation-based resonance form. But in case of nucleophilic aromatic substitution reaction, you can prefer the negatively charged resonance form during the reaction. And the nucleophile adds to the aromatic ring to offer a delocalized anion form which the leaving group is eliminated. Later, the leaving group is leaves out, gives an end product of substituted through SNAr mechanism. To simplify this, take an electron withdrawing group carrying the substrates and which has a leaving group, and try to use a nucleophilic substitution reaction on this kind of aromatic halides. Then once the nucleophile attack over here, particularly the carbon which is carrying the leaving group, and the shifting of bond, aromatic bond, will shift over here, next carbon, and it carries a negative charge. And you can write down the 3 resonance form corresponds to this by shifting over here and this over here. You will get this particular resonance form, and you can shift over the negative charge over here, and this can shift over here. During the shift, this can shift over this particular carbon. Okay, so now the only thing is the leaving groups needs to leaves out, as it is a better leaving group. Then only you can expect a new substituted product over the aromatic system. The delocalization of negative charge can occur only when the nucleophile adds to the ortho or para position with respect to the electron withdrawing group. So in as nucleophilic aromatic substitution reaction, you can expect the nucleophiles to attack. In this case, this is an para positioned leaving group. Para position with respect to the electron withdrawing group, you have a para position, the leaving group is present. Or you can have a substrate. In such cases, the ortho positioned leaving group can also be present. In such cases, nucleophile can also be attack over the leaving group where the present in the ortho position with respect to electron withdrawing group. And those 2 types of substrates can be easily performed via SNAr mechanism. So ortho position and para position with respect to the electron withdrawing group are they preferred. The addition to the meta position gives an adduct stabilized by the inductive effect, but not the mesomeric effect. Therefore, towards nucleophiles, electron withdrawing group are activating, and electron withdrawing group are activating and ortho para orienting, and in contrast, electron donating group deactivate and meta directing. These principles are opposite of these that apply to electrophilic substitution reaction. So you need to have an electron withdrawing group. You need to have an electron withdrawing group if you want to perform an SNAr reaction. And the leaving group always present over the ortho position or at the para position. Then only you can expect the SNAr reaction, because it will stabilize the formed negatively charged resonance during the mechanism. Then SN1 mechanism, let's move on to the SN1 mechanism. This mechanism operates in a reaction of diazonium salt with nucleophiles. The driving force resides in the strength of the bonding in the nitrogen molecule that makes it a particularly good leaving group. Suppose if you have these kind of substrates, diazonium based substrates, then dissociation of the CN bond, you will get a positively charged benzene, and this first step is the slow step actually, diazonium salts, then attack of the nucleophile over the form the carbocation, and the attack of water molecule over this particular species is a fast step, and you will get the OH2 plus As it is a lone pair is involved, one of the lone pair is involved in the bond formation, oxygen prefers to carry a positive charge. Then the oxygen doesn't prefers to carry a positive charge. In such cases, the deprotonation is the only method to overcome this positive charge, and minus H plus will leaves out from the system, and you will get an phenol as an end product. So the diazonium salt, if you are having a substrate, and you can also perform SN1 mechanism. In this case, SN1, Y means 1. This is forms a stable reaction intermediate of benzyl cation, what is it? No, phenyl cation. Then the nucleophilic attack, it's in two-step fashion, similar to that of the SN1 mechanism. That's why you can call it as SN1. The formation of carbocation and then followed by the nucleophilic attack, which leads to the formation of the alcohol, phenol. The mechanism operates in reaction of diazonium salt with nucleophiles. The driving force resides in the strength of the bonding in the nitrogen molecule. That makes it particular good leaving group. And I think this benzyne mechanism you have covered in the degree level, it seems. Aryl halides. Aryl halides that have no activating groups proceeds reactions with a strong base to give benzyne intermediate, which undergoes reaction with nucleophile to give a mixture of regioisomers. And take the benzyl chloride, then you need to use a strong base NH2 minus, and deprotonation will taken place from the ortho positioned hydrogen atom, then shifting of this bonded electron, and simultaneously knocks out formation of benzyne as an intermediate. Then comes the nucleophile needs to attack either from this particular position, the C14 labeled carbon, or the nucleophile can attack over this particular carbon, which leads to the two types of product. In this case, the C14 and this particular product formation is different, because you have started with the isotopically labeled carbon over the carbon which is attached to the Cl. Suppose if you are not using the isotopically labeled carbon, in such cases, whatever you will get is aniline only. The position is doesn't matter. You will get the aniline. So conversion of the chlorobenzene to the aniline using sodamide. This proceeds via benzyne mechanism. So the benzyne is, the reaction intermediate is benzyne. This is the benzyne formation, and then followed by the nucleophilic attack over the benzyne, which leads to the formation of corresponding aryl amines. Okay, so I think with this I will stop here.